Right, so now we're into the last section of the syllabus for sets, relations, and groups, which is 4.12, and we're going to be talking about homomorphism and isomorphism. So let's start by defining homomorphism, isomorphism, kernel, and range. So you can see that definition of a kernel, this is all part of your syllabus. And again, the proofs that you need to know are also listed in your syllabus. So both a homomorphism and an isomorphism are built off of three things: two groups as well as a function. And so the way that it works, we've got our two groups. So we've got some group we'll call G with some operation star. We've got some group H, and we'll call its operation blob. And then we have some function that takes G and maps it onto H. If this function has the property that f of A star B is the same as f of A blob f of B, so notice here we first do the star and then put it in the function. We do the function of A, do the function of B, and then blob them together with whatever operation that is. So if this is true, then we have a homomorphism. So all of this makes a homomorphism. If f is a bijective function as well, then we have an isomorphism. And we've looked at isomorphisms before, those being groups that have elements that have the same order and their Cayley tables can be represented in the same way, even if the elements are not necessarily the same. So what we're looking at is groups with the same structure. Yeah, that's what homomorphism and isomorphism is. It's super helpful because we can take a simpler group, and if we know it's isomorphic to a more complex group, then we know properties of the more complex group based on the simpler group. It's one of the ways that Fermat's last theorem was proven in 1994. And Fermat's last theorem was developed in the mid-1600s. So finally, we've got a reason for group theory. All right, so we've got homomorphism and isomorphism defined. We need to find the kernel. So the kernel is a set of elements. So it's the set of elements in G that map to H through the function, the set of elements from G that map using F from G into the identity elements of H. So we're mapping through our function F. The range it's the range of the function F, and it's the set of elements of H that are mapped to by G. By the elements in G. So this is very similar to our normal definition of range. Kernel is the different one. So we've got our set elements from G that map to the identities of H. All right, so those are the basic definitions. We're going to come back in other videos to look at problems using this.